right, we are ready for our second talk of the technology track. Thanks again for joining. Our next speaker is Nanci Hardwick. She's the CEO of Meld, M-E-L-D, the Manufacturing Corporation, Meld Manufacturing Corporation and AeroProbe Corporation. Meld has changed the scale of metal additive manufacturing with its solid-state printing process. Nanci has led Meld from a concept to commercialization with several awards, including R&D 100's Most Disruptive New Technology worldwide and the Edison Award. The company holds over 24 patents and manufactures industrial meld printers capable of printing aluminum, magnesium, copper, titanium, steel, and more. AeroProbe provides the aerospace industry with air data systems designed to improve safety and performance of unmanned aerial vehicles. AeroProbe also designs, manufactures, and collaborates multi-hole probes used by researchers around the world for design validation. Nanci was the founding member and board chair of the AUVSI Ridge and Valley chapter. She's the board chair for Rona-Blacksburg Technology Council. She's got a lot of different positions. I won't go through them all. But she's an amazing, amazing woman and received so many awards. We are so grateful to have you today. Thank you so much, Nanci, and take it away.
Thank you, Amy. Can you let me know if you can see my slides?
Yes, ma'am. We are good to go. You look great.
Thank you. All right, fantastic. Okay, well, thank you for the opportunity to be here. I'm really excited to share my company and our technology and this program with so many of you, and I'm just grateful to be part of the conversation. I know that not everyone has become acquainted with the Meld technology yet, so I'll start by saying we are located in Virginia in the United States. This is a newer company. We were founded in 2018 and have come to market with printers and services using the patented Meld technology. What's different about Meld is that it is solid state. The material stays below the melt temperature, and this enables a lot of great attributes for the printing itself and also for the parts that are printed. So before I start with a video showing you, I'll ask you to note a couple things as you watch, and then I'll let you just watch. One of the things about staying below the melt temperature is we're keeping all things at a low temperature. And so when you watch this printing video, you'll notice we're printing on a very thin substrate that is very simply fixtured, and there is no distortion. In fact, when the part came off after printing, it was as flat as you'll see it in this video. So here's your substrate, simple fixturing. And then you'll also notice right away that we're in open air, making this very large part. 10-foot cylinder in aluminum 6061. I heard someone just ask Miranda about that. So we are printing here in the 6000 series, and that's about 3 meters in diameter. So we'll stop here and explain what's happening in the process. We have a nice close-up view at the point of deposition. So this schematic will help us explain it. As you can see in the bottom right, we're moving material through a hollow tool. So really simple concept. This material is under force in the z-axis and also is benefiting from shear forces that are created during the rotation of the tool. This allows us to put enough energy into the material that we're printing for it to plastically deform, and simultaneously to put energy into the material we're printing onto for it to plastically deform just under the point of deposition. This allows these two materials to literally be stirred together. You can see discrete layers here as you stand on the outside of the part, but this outside edge will be machined away. And if we were to look at a cross section of that material after the machining away of this exterior skin, we wouldn't even be able to tell that it had been 3D printed. There would be no evidence of these layers. The microstructure will be uniform through the layers and in every direction of the print. So one of the great things about the meld process is that we are printing fully dense material. We're done once it's printed, and we're able to print, as you can see, in high volumes. So in terms of the program and the opportunities that Meld offers, and in fact where Meld's place is as a process in the AM market, it all comes down to the fact that it's a no melt. And so just another tool in the toolkit, and really on one end of the spectrum in terms of size and print rate. We make trades all the time, and so we can talk about some of those in a bit. You saw the high print rate. We talked about fully dense, wrought properties, great properties from the printed material, and we talked about its simplicity. The great thing about a simple process is that it lends itself to predictability and repeatability. And we'll talk more about what you can print with, but this technology has so much freedom for the user, so much flexibility. This is a great time to navigate around supply chain challenges with the materials available to us. And we looked at a record-breaking part being built. We feel big is beautiful, and that meld was made for parts measured in meters, not millimeters. And one thing that I'm personally very excited about is the opportunity with the same machine, with the same process, to conduct repairs. Whether it's cast parts, forged parts, it doesn't matter. You have an opportunity to put a part on a machine in open air and add back material. And with sustainability being top of mind for all of us, this is a great tool for that. So let's talk about how this technology is being used for the world's largest printer, and how big is the world's largest printer, and whose printer is it? This is something that we're so excited to be a part of. There's a team of people working on it, but ultimately it's being led by the U.S. Army. And some of the information I'm about to share is courtesy of the Army. The program is focused on and is designing and manufacturing now a printer with a build space of 20 feet by 30 feet by 12 feet in height. So the equivalent is just over 6 meters by 9 meters by almost 4 meters in height. Really mind-blowing dimensions. So with this printer and with the Meld technology, we will be printing parts at a scale never seen before. And when I say parts, this is what I mean. I mean entire ground vehicles. Very, very excited to share this with you all. The program is referred to as the Jointless Hull program, and really this slide and these graphics explain what that means. The desire is to take advantage of what additive manufacturing has to offer to ultimately save lives, because there are humans inside these vehicles. and to leverage all of the flexibility in design, the new alloys, and in some cases, the speed to deployment that additive can offer. So the program's objectives are very simple: to build a tool that allows printing at this magnitude, to develop the qualification and expertise in parts and alloys using this technology at this scale, to utilize the Center of Excellence for Advanced Manufacturing at Rock Island Arsenal for the printer, the development, and also to leverage a smaller scale printer in which some of the qualification activities can be conducted, and then to print and to utilize this technology. So when we think about, and in fact, what was shared, the considerations for which technology should be leveraged for a printer of this scale, many of the same objectives that probably all of you consider in your manufacturing responsibilities were considered. Size, it needs to be a technology that can print parts of this size. When we're talking about gigantic parts, speed of print matters, and materials is a special consideration here because this is a tool for generations to come to leverage. So it needs to be able to use today's materials, tomorrow's materials, and the future's materials. And this is something that Meld was uniquely able to offer to the program. Quality and performance are always of utmost importance, as is cost. And cost is something that is about the process itself, about the logistics around the process, about the infrastructure for the process, how much power, for example, it might take, or if it requires atmospheric shielding, but it's also about the raw materials. And one of the great things about the meld process is that off-the-shelf material can be used. So as I mentioned, these are solid rods that go into the printer, not powder, not wire, not a material whose chemistry was especially developed for additive. The last and unique attribute that was considered for this particular program was the ability to make a jointless hull. And that came from an awareness that joints created by welding created opportunities for weakness and ballistics resistance, and a desire to have a uniform microstructure, a uniform build from the bottom up, and that's something that the meld process can do. So these are some of the considerations and some of the reasons why this solid state process is really well suited to be the additive tool to go on a large format machine that will also be subtractive to build these jointless vehicle hulls. Some of the other things that were considered and observed about the technology during the competitive process in which it was selected was the demonstrated ability to make complex geometries and also to build larger components with very thick wall thicknesses. And here again, we can see open air printing and that stirring action. We talked previously about the dynamic recrystallization that occurs at the point of deposition. What this allows is grain refinement, and grain refinement has a lot of good properties and outcomes for performance. So I'll give you an example here. We're looking at the before and after of an aluminum 7075. And these EBSD images are both using the same scale. So on the left is an image of the material that would have been used in the printing. And on the right is an image of the material that was printed. And you see some just extreme grain refinement here. In all cases, we see grain refinement in the printing of the meld parts. And this is always uniform in all directions, and that equiax grain structure is beneficial. Usually smaller grains translate into performance attributes like greater wear resistance, greater corrosion resistance, and often greater strength. And this is a contributor to what we see in materials where we have qualified against forging standards. And this, of course, was of great interest to the Army in the selection of meld for the printer as well. So aluminums, magnesium great for lightweighting, titanium great for lightweighting, but stainless steel, nickel-based super alloys, all printing to a forged standard. And I know it was asked about aluminum 6000 series in the previous presentation, and that is something we can do. That's one of the great things about a non-fusion based process is so many more alloys are available to us to print. And you can see here a 7075, but 2000 series as well. These are fantastic alloys, especially for the aerospace industry who is interested in utilizing them for lightweighting. And lightweighting is something that is relevant not only to aerospace, but to space, to ships, to trains, to ground vehicles. Lots of opportunity around these alloys, and now we can really unlock their potential by combining them with a 3D printing technology. So how we do our testing to confirm isotropic properties is perhaps take a build similar to the one we just saw and harvest many samples from it. Here showing samples from the XYZ, what those look like after they're machined. They go off to a third-party lab or customer lab or our own lab, and tensile testing is done to look at the ultimate tensile strength, yield strength, and elongation. And then these in quantity are compared against the standard, and this is essentially how a qualification program is conducted. There are many more attributes to qualify against, but this is always a great baseline. So very much of interest and something that we'll be seeing done on customer printers and these Army printers as well. But as I mentioned, the most important thing that we can offer is the ability to have the user print any material that they would like. And we've certainly demonstrated many at our facility in Virginia. This is an ever-growing list, and at this time, there's no known limit to metals that can be printed with meld printers. So in terms of future-proofing, this technology has a lot to offer to allow for growth and innovation in other areas. Another consideration for the Army was that Meld already is producing off-the-shelf printers. This is one of our smaller printers, the L3. You can see easy to use user interface, lots of build volume. It's about 14 cubic feet. The next size up that we offer today is about 82 cubic feet, and we're about to launch an even bigger printer this year, so stay tuned for that. Having a lot of knowledge about materials and and Meld performance is difficult with a new technology. So I've shown you some of the things that we've done. It has been helpful to have the credibility of such great organizations awarding the technology and the company honors since we got started in 2018. So this has definitely helped us to demonstrate what's possible. Of course, nothing says it like printing things. So these are some of the initial parts that we were able to print for the Army in conjunction with this program. And you're looking at a near net shape of a vehicle component here. This is what we used to think of as a big part, but now we know they'll be even bigger very soon. And just to show how important it is to be able to take ideas from concept to printer, I wanted to show everybody. I'm sure you're familiar, but if you're not, it's nice to see what a slicer can do. So it's important for Meld customers to be able to take their parts from a CAD model, for example, and move it through a program that helps define how it will be built on the machine. So this is the part we just looked at, and we're going to see it being built layer by layer in the slicer software environment. And actually what we're watching is the tool path. So this is 2 tracks overlapping each other per layer on the build. And what that looks like in reality is this. And so this is a great demonstration of how you can build even bigger wall thicknesses with the ability to do overlapping tracks. This is something that we would have tested out at our facility, determined how much overlap is needed, and then done some analysis just like we looked at to verify that that material in that overlap area has the same quality as the material of a single track wall. So these printers are standard off-the-shelf metal rod. We do have printers in our facility that use powder, and we have demonstrated the ability to recycle materials with those. So there's a lot more that the Meld technology has to offer. It's been really great in our facility to be able to run these printers in an open air environment. The solid rod filler material allows us to completely eliminate powders from our facility. So we eliminate a lot of safety equipment that is necessary to manage powders, and we eliminate the hazards. Without atmospheric control around this machine, we are also operating in a very green way, limiting the use of gases, and it's a very low power process. This is basically a CNC machine that puts the chips back on. We build the part in a very machine shop-like environment with machine shop-like tools, and our operators are former CNC machinists, so it's really very easy to use. So as I said, this is what a big part used to look like. This is what a big part is going to look like, and this is what a big printer is going to look like. This printer stands at 42 feet tall. It will come online at the end of this year. I'm very excited to give you a picture of me standing in front of this machine, but pointing out to you, here's what a 6 foot tall human looks like. So just give yourself a moment to put yourself right there and imagine watching that part being printed by this equipment. And if we look at that part that's being printed there, I'll bring it full circle back to where we started, which is here. So this is printing at a scale just never before imagined. I couldn't be more excited about it. The Army believes that this will be a game changer, and so do I. Thank you so much for letting me share it with you.
Thank you. That is just mind-blowing. I cannot wait to see this technology. And I'm not that far from Blacksburg, so I want to come see it. So
please come.
Let me know. Awesome. All right. Well, we have several questions for you. We'll try to get through them as quickly as we can. The first question is, when considering size, especially at that scale, what are the tolerances that can be held, i.e. how much material needs to be machined off to obtain the final desired dimensions?
Yeah, that is a great question, and one every customer asks us. So we have some ability to control our track width. Our minimum track width might be 1/4 inch. Our maximum track width might be 2 inches. So quite large. Oftentimes, a part wall thickness might vary more than the meld wall thickness. So we find that we are operating really inside some wide tolerances when we nest the finished part in the meld model. We have usually a margin to spare. That exterior that gets machined away is very small, maybe 1/10 of an inch, but it does depend on the material being printed.
And along those lines, what is the least achievable wall thickness, or I guess the thinnest wall thickness?
Yeah, I don't know what the thinnest is. Like I said, to date, it's been about 1/4 of an inch, but ever since we got started with this technology, there's been a demand to go bigger and not a demand to go smaller. So our efforts have been on scaling up. I don't know how much we can scale down, but I hope to get the chance to find out one day.
The next question is, how do you deal with oxidation?
Yeah, that's the great thing about the melt process is staying below the melt temperature really removes the risk of oxidation. So it's an opportunity to just come at printing from a completely different way.
Let's see. What's the maximum overhead you can do?
Also, don't know the answer to the maximum, but we have done about 45 degrees.
And is there a difference between this process and friction stir welding? I think is the question.
Yeah, great question. A lot of similarities, but there is a big difference. Friction stir welding is not additive and cannot be additive, and meld is additive and cannot not be additive. So friction stir welding is great for combining existing material, 2 plates, for example, and meld is great for adding material.
All right, we'll take one more question. This one's a little cheeky. It says, is it really jointless since every single layer is technically joined together by welding?
Yeah, so thank you. I appreciate the opportunity to clarify that every single layer is not joined by welding. It's joined by meld, and meld is so different from welding because we're not melting. And really where one of the places where that offers an advantage is at the interface. So there is no interface in between 2 layers. In fact, as I said, if we cut the material apart and have a look at it and evaluate it, we won't be able to see where the layers were at all. So yeah, it's really different, and it takes a little bit of time to wrap your head around what's happening. And so, yeah, thank you for the opportunity to share it.
Awesome. Thank you so much. We'll go ahead and step off the stage and get ready for our next speaker. Thanks again, Nanci.
Thank you.